Picture a world where rings of ice and dust stretch hundreds of thousands of miles wide, casting shadows across a swirling golden atmosphere. A planet so massive it could swallow 700 Earths, yet so light it would float in an ocean, if such an ocean could exist. This is Saturn, the crown jewel of our solar system, a place where beauty and mystery collide in ways that still leave scientists speechless. For centuries, we've gazed at its dazzling rings through telescopes, sent robotic explorers to skim its clouds, and yet, this gas giant refuses to reveal all its secrets. What lurks beneath its tempestuous storms? Why do some of its moons spew geysers into space, while others hide oceans that might harbor life? And perhaps most haunting of all, what cosmic forces sculpted those iconic rings, and how long will they last? Today, we're embarking on a journey to uncover 25 of Saturn's most bewildering enigmas, phenomena that defy explanation, challenge our understanding of physics, and sometimes hint at possibilities so strange they seem ripped from science fiction. From hexagonal storms larger than our planet to moons that shouldn't exist, each mystery peels back another layer of this celestial marvel. Some clues come from NASA's Cassini mission, which spent 13 years orbiting Saturn, while others emerge from mathematical models that collapse under Saturn's contradictions. And yet, with every answer we grasp, new questions spiral into view, leaving us humbled by the universe's endless creativity. This isn't just a tour of scientific anomalies, it's an invitation to stand at the edge of the unknown. To witness the moments when astronomers gasp at their data, when theories crumble, and when nature whispers hints of truths we're only beginning to fathom. Whether you're a lifelong space enthusiast or someone who simply marvels at the night sky, these mysteries remind us that wonder isn't just for scientists, it's woven into the fabric of the cosmos, waiting for anyone daring enough to look up and ask, what if? So let's begin where curiosity outshines certainty, in the shadow of Saturn's rings, where the next great discovery might be hiding in plain sight. Deep within Saturn's swirling golden haze, a shape emerges that shouldn't exist, a near-perfect hexagon, so precise it looks carved by some celestial architect. This six-sided storm, larger than Earth itself, has raged around the planet's north pole for at least 4 decades, maybe longer, defying every expectation of how fluids behave in nature. Atmospheric scientists still rub their eyes at the data. Storms on Earth twist into spirals, Jupiter's cyclones churn in tangled ovals, yet Saturn's north pole hosts a polygon so geometrically crisp, its angles could have been drawn with a protractor. What makes this hexagon even stranger is its persistence. Unlike hurricanes on our planet that weaken over days or weeks, this structure has maintained its shape while whipping winds at speeds over 300 miles per hour, fast enough to lap Earth's jet streams twice over. Even more perplexing, the hexagon isn't just a surface feature. It plunges hundreds of miles deep into Saturn's atmosphere, like a titanic honeycomb cell spinning through the clouds. So how does nature sculpt such a freakishly stable geometric storm? One leading theory points to standing wave patterns in Saturn's atmosphere. Imagine ripples in a spinning cup of coffee, but scaled up to planetary dimensions. Gas layers moving at different speeds might create interference patterns that lock the hexagon in place. Others speculate it's driven by deep-rooted jet streams, shaped by Saturn's rapid rotation and lack of solid landmasses to disrupt the flow. There's even a wild-card idea involving convection currents rising from the planet's interior, stacking like layers of an invisible cake to stabilize the angles. Yet every explanation hits a snag. Computer models struggle to recreate the hexagon's razor-sharp edges without them blurring into chaos. And while lab experiments using spinning fluids have produced fleeting polygons, none match Saturn's marathon stability. It's as if the planet is taunting us with a riddle written in hurricane-force winds, one that challenges our grasp of fluid dynamics, planetary physics, and perhaps even the boundaries of what we consider possible in nature's playbook. The hexagon isn't just a scientific curiosity, it's a living laboratory. By studying how it consumes energy, shifts over time, or even how its dark central vortex, a hurricane twice the size of Earth, dances within those geometric walls, we might unlock secrets about atmospheric behaviors far beyond our solar system. After all, if a gas giant can grow something this precise amidst the chaos, what other impossible shapes might lurk in the skies of distant worlds? If Saturn's hexagon feels like a defiance of physics, its moon Enceladus plays by an entirely different rulebook, one where frozen worlds aren't supposed to fizz. This tiny, gleaming moon, barely 300 miles across, should be a silent ball of ice, frozen solid in the depths of space. Instead, it's erupting. Towering plumes of water vapor and organic compounds blast from its south pole like galactic geysers, shooting hundreds of miles into space with enough force to feed one of Saturn's faint outer rings. It's as if Enceladus is exhaling secrets into the cosmos, and what it's whispering could rewrite our search for life beyond Earth. The source of these geysers is perhaps even more astonishing than the eruptions themselves. Beneath Enceladus's icy crust lies a global ocean, not a frozen puddle, but a liquid saltwater sea, kept warm by the moon's constant flexing as Saturn's gravity kneads it like dough. This subsurface ocean isn't just wet, it's chemically rich. When NASA Cassini spacecraft swooped through the plumes, it detected hydrogen, carbon dioxide, and methane, ingredients that, on Earth, feed entire ecosystems around hydrothermal vents. Even more tantalizing, tiny silica nanoparticles, the kind that form when hot water interacts with rock, hinting at geothermal activity on the seafloor. Here's where the mystery deepens. Life as we know it requires three things: liquid water, essential chemicals, and an energy source. Enceladus checks all three boxes. Those hydrothermal vents might be churning out energy-rich compounds, just like the ones in Earth's oceans where life thrives in utter darkness. But how does a moon so small, smaller than the state of Arizona, maintain an ocean for billions of years, and what could possibly be fueling those explosive geysers? Some researchers think tidal forces create cracks in the ice, allowing water to burst through like a pressurized soda can. Others suggest the ocean itself might be fizzy, packed with dissolved gases that erupt when the ice fractures. Then there's the question we're all itching to answer: could something be alive down there? Enceladus's plumes don't just contain water and salts, they're laced with complex organic molecules, the building blocks of life. No one's claiming we've found aliens, but this moon has vaulted to the top of astrobiologists' wish lists. Future missions like NASA proposed Enceladus Orbiter aim to fly through those plumes with sensors fine-tuned to sniff out biosignatures, molecules that scream life was here. What makes Enceladus extraordinary isn't just the possibility of life, though. It's the sheer audacity of its existence, a moon that sprays its ocean into space, offering free samples to anyone flying by, is breaking every rule we thought we knew about icy worlds. Every geyser is a challenge, a dare to explore further, because if life can thrive in the dark, churning depths of an alien moon, where else might it be hiding? Saturn's F-ring isn't just another band of ice, it's a cosmic ballet, a twisting, braided ribbon that dances to the gravitational tune of two mischievous moonlets. While most of Saturn's rings behave like orderly highways with particles gliding in smooth, predictable orbits, the F-ring is a rebellious whirlwind of kinks, clumps, and spirals, as if it's constantly rewriting its own rules. What makes this narrow ring so chaotic? The answer lies in its tiny shepherds, Prometheus and Pandora, moons no larger than cities, whose gravitational tug-of-war stretches and sculpts the F-ring into shapes that baffle astronomers. Prometheus, the inner moon, is the ring's primary puppeteer. Every 17 hours, as it swoops closest to the F-ring in its lopsided orbit, Its gravity claws at the icy particles, dragging tendrils of material outward like taffy. These streamer channels can stretch hundreds of miles before snapping back, leaving behind braids and knots that linger for weeks. Pandora, orbiting just outside the ring, plays counterpoint, herding stray particles back inward with her own gravitational nudges. Together, these moonlets create a dynamic squeeze and release effect, a celestial tug of war that keeps the F-ring in perpetual upheaval. But the moonlets aren't the only artists here. The F-ring's particles themselves seem alive, colliding in ways that birth bright, transient mini-jets, sudden bursts of debris that streak through the ring like fireworks. Some of these features vanish within days, others grow into massive clumps miles wide, defying models that say such structures should dissipate instantly. Even more puzzling are the ring's spokes, ghostly radial shadows that flicker across its surface, as if some unseen force is sketching on it with invisible ink. The deeper mystery: this shouldn't be stable. Classical physics predicts the F-ring's chaotic dance should have torn it apart eons ago, scattering its material into space or merging it with neighboring rings. Yet here it is, thriving on the edge of chaos, a testament to the delicate balance between destruction and creation. Some scientists speculate hidden moonlets, too small to spot, might be stirring the pot further. Others wonder if the ring's own particle collisions generate enough collective gravity to hold it together against the odds. What's clear is that the F-ring isn't just a curiosity, it's a real-time laboratory for studying how celestial bodies interact. Every kink and braid holds clues about the birth of solar systems, where dust and gas once swirled into planets under similar gravitational choreography. And as we watch Prometheus and Pandora sculpt their icy masterpiece, we're reminded that even in the vastness of space, the smallest players can create the grandest spectacles. Saturn's iconic rings, those dazzling bands of ice and dust that have inspired astronomers for centuries, are vanishing before our eyes. Right now, an invisible rain is falling, torrents of ring material plummeting into Saturn's atmosphere at a rate that could fill an Olympic-sized swimming pool every half hour. NASA Cassini spacecraft made the chilling discovery during its final, suicidal dive between the planet and its rings. Charged water molecules, pulled downward by Saturn's magnetic field, are creating a literal ring shower. This cosmic downpour means Saturn's most famous feature might be on borrowed time, with estimates suggesting the rings could completely disappear in just 100 million years, a blink in cosmic terms. What's startling isn't just the rings' impending demise, but what their rapid decay reveals about their past. If the rings have been shedding material this aggressively their entire existence, they likely formed far more recently than Saturn itself. While the planet is roughly 4.5 billion years old, the rings might be a mere 100 million years young, dating back to when dinosaurs still roamed Earth. This challenges the long-held assumption that the rings formed alongside Saturn from the solar system's primordial debris. Instead, they might be the shattered remains of a comet or moon that ventured too close and was torn apart by tidal forces, a celestial accident frozen in time. The ring's fleeting nature raises another haunting question. Why are we here at just the right moment to witness them? Saturn's rings span nearly 200,000 miles, yet they're barely as thick as a 3-story building. In cosmic terms, they're a transient spectacle, like catching a soap bubble mid-pop. Their youthful age suggests we're living in a special era, one where Saturn wears its crown, but future civilizations might gaze at a bare, ringless giant. But the mystery doesn't end there. Some researchers argue the rings could be older, their material constantly replenished by moonlets colliding within them. Others point to the rings' surprisingly clean ice, relatively untouched by space dust, as evidence of their youth. Every answer seems to lead to new contradictions, leaving scientists scrambling to explain how such a majestic structure could be both so ephemeral and so pristine. What's certain is this: Saturn's rings are teaching us that even the grandest cosmic wonders have expiration dates. Their fleeting beauty reminds us that the universe is ever-changing, and that sometimes the most profound discoveries come from watching something disappear. Among Saturn's many strange satellites, Hyperion stands out as a cosmic oddity, a moon so riddled with holes it resembles a celestial pumice stone. Unlike the smooth, round worlds we're accustomed to, this tumbling, potato-shaped object is pockmarked by colossal craters with walls so deep and porous, sunlight sinks into them like quicksand. If you could stand on Hyperion's surface, you'd weigh almost nothing, because this moon is barely more than floating rubble, with a density so low it might be half empty space inside. What created this spongy nightmare? One leading theory suggests Hyperion is a survivor, a fragment from a catastrophic collision that shattered a larger moon billions of years ago. The debris, loosely held together by gravity, never fully compacted, leaving gaps like a poorly packed snowball. Others propose an even wilder origin. Hyperion might not be native to Saturn at all. Its erratic orbit and composition, laced with organic compounds, hint it could be a captured comet or asteroid, a wanderer snagged by Saturn's gravity and trapped in its cosmic menagerie. Then there's the moon's bizarre rotation. Unlike most moons, tidally locked to their planets with one face always forward, Hyperion tumbles chaotically, its axis flipping unpredictably as it orbits. This isn't just a slow wobble, it's a full-blown celestial seizure, with the moon's orientation shifting dramatically from one pass to the next, the culprit. Saturn's largest moon, Titan, whose gravitational kicks delivered every few orbits, send Hyperion into a dizzying spin. But the real enigma lies beneath those gaping craters. When NASA Cassini probe zipped past Hyperion in 2005, its instruments detected something shocking. The crater's floors are electrically charged, crackling with static that may repel loose particles, preventing them from filling the voids. This could explain why Hyperion's craters stay so pristine, even as micrometeorites bombard it. Some scientists speculate this electric field might even be lofting dust off the surface, creating a faint, ghostly halo around the moon. Hyperion's fragility raises a haunting question. How does it survive at all? Most loosely packed bodies in the solar system, comets, rubble-pile asteroids, eventually disintegrate under tidal forces or collisions. Yet Hyperion endures, a delicate fossil from the solar system's violent past. Every weird groove and cavern is a time capsule, preserving clues about the chaos that shaped planetary infancy. And as it continues its drunken dance around Saturn, it reminds us that sometimes the universe's greatest mysteries aren't just about what's there, but what's missing. Of all Saturn's moons, none plays dress-up quite like Iapetus, a world split down the middle, with one hemisphere black as charcoal and the other bright as fresh snow. This yin-yang moon doesn't just hint at contrast, it's a cosmic optical illusion, with the dark side absorbing sunlight while the bright side reflects it so intensely. The difference in albedo is sharper than any other known object in the solar system. Standing on the border between these two realms, you'd witness a sunset unlike any other, one half of the sky swallowed by endless twilight, the other glowing like a frosted mirror. The leading theory for this duality reads like a celestial crime scene. Saturn's distant, dark-coated moon Phoebe, orbiting backward against the flow of its siblings, sheds dust like a crumbling comet. As these particles drift inward, they're swept up by Iapetus's leading face, the side that plows forward in its orbit, painting it darker over eons. But here's where the plot thickens. The dark material, mostly carbon-rich compounds, absorbs sunlight and heats up, causing underlying ice to sublimate. This vapor then migrates to the colder, brighter trailing side, where it recondenses as fresh frost, amplifying the contrast in a self-reinforcing cycle. It's a feedback loop written in ice and shadow, where darkness begets more darkness and brightness intensifies itself. Yet not all scientists are convinced this external dusting tells the full story. Some argue Iapetus's dark stains might also arise from within. Volcanic activity, or more accurately, cryovolcanism, could have once spewed methane or other hydrocarbons from the moon's interior, which then reacted with sunlight to form dark, tarry deposits. Others point to the eerie precision of the dark region's borders, which align almost perfectly with the moon's leading hemisphere, as if an invisible force field shields the rest. Could Iapetus's own weak magnetic field, or even electrostatic forces, be funneling incoming dust to specific zones? The moon's bizarre equatorial ridge adds another layer to the puzzle. Stretching like a giant seam around its middle, this 12-mile-high mountain chain gives Iapetus the appearance of a cosmic walnut. Some suggest the ridge might be remnants of a shattered ring system that collapsed onto the surface, while others propose it's the scar of a frozen-in-place tectonic upheaval. Remarkably, the ridge is most pronounced within the dark terrain, as if the two mysteries are entangled. What makes Iapetus truly extraordinary isn't just its appearance, it's the defiance of expectations. Moons aren't supposed to be this asymmetric, this geometrically stark. Yet Iapetus flaunts its duality like a challenge, forcing us to reconsider how dynamic even frozen worlds can be. Every patch of darkness, every gleaming plane, is a clue in a detective story spanning billions of years, and we're only just turning the pages. Saturn doesn't just have winds, it has supersonic hurricanes that rewrite the rules of atmospheric physics. Imagine a storm so fast it could circle Earth's equator in under 5 hours, with jet streams screaming at up to 1,100 miles per hour, 3 times the speed of Earth's fiercest tornadoes. These aren't fleeting gusts, they're planetary-scale rivers of gas, weaving around Saturn's equator and poles with the precision of a lathe, yet no one knows exactly what keeps them revving at such impossible speeds. The puzzle isn't just the velocity, it's the engine behind it. On Earth, wind patterns are shaped by mountains, oceans, and friction with the ground. But Saturn has no solid surface, just an endless abyss of hydrogen and helium deepening into metallic slush. Without terrain to disrupt the flow, its winds should theoretically lose energy, like a spinning top slowing on a frictionless table. Yet Saturn's jet streams have raged for centuries, if not millennia, as if some invisible hand is perpetually cranking the throttle. One clue might lie in the planet's internal heat. Saturn radiates 2.5 times more energy than it receives from the Sun, suggesting some process, perhaps helium rain sinking through liquid hydrogen or residual heat from its formation, is stirring the atmosphere from within. Picture a pot of boiling water but scaled to planetary dimensions, with convection currents churning the gas layers into motion. Yet even this doesn't fully explain the wind speeds. Some models propose that Saturn's deep interior rotates slightly slower than its visible cloud tops, creating shear forces that amplify the jets like a cosmic dynamo. The real curveball, Saturn's winds aren't uniform. They're layered like an onion, with adjacent bands blasting past each other at different velocities. Near the equator, the superfast jet stream narrows to a razor-thin ribbon, while at higher latitudes, winds reverse direction entirely, creating swirling turbulence. This complexity hints at a hidden interplay between the planet's internal heat, its rapid rotation. A day on Saturn lasts just 10.5 hours, and even its colossal storms, which may dredge up energy from deeper layers. Then there's the wild card, Saturn's rings. Recent research suggests ring particles crashing into the upper atmosphere might inject energy like grains of sand kicked into a fan. Others speculate that the planet's magnetic field, interacting with charged particles in the ionosphere, could generate currents that nudge the winds forward. But every theory has gaps. Simulations struggle to replicate Saturn's wind patterns without adding phantom forces, leaving scientists to wonder if we're missing a fundamental piece of atmospheric physics. What makes these winds so mesmerizing isn't just their speed. It's what they reveal about gas giants across the universe. If we can crack Saturn's secrets, we might finally understand why some exoplanets light years away sport even faster gales in their soupy atmospheres. For now, though, Saturn's winds remain a humbling reminder that even in our own solar system, nature still holds the best cards. Every 30 years or so, Saturn does something extraordinary. It coughs up a storm so vast it could swallow Earth whole. Known as the Great White Spot, these tempests erupt with such violence, they're visible from telescopes on Earth as a brilliant white scar slashing across Saturn's golden haze. Unlike hurricanes confined to one region, these megastorms wrap around the entire planet like a noose, stretching over 15,000 miles wide and churning for months before fading into the clouds. What's bizarre isn't just their scale, it's their eerie punctuality. Since 1876, astronomers have documented 6 of these events, each arriving roughly every Saturnian year, as if the planet's atmosphere is set to some cosmic alarm clock. The secret to these storms might lie in Saturn's seasons. A year on Saturn lasts 29.5 Earth years, with each season dragging on for over 7. As the planet tilts toward or away from the Sun, sunlight shifts across its latitudes, warming layers of atmosphere unevenly. Scientists suspect this slow solar heating acts like a pressure cooker trapping energy beneath Saturn's upper cloud decks until it violently bursts through like steam blowing a lid. But here's the twist. The Great White Spot always erupts in Saturn's northern hemisphere during its late summer, suggesting some seasonal trigger we don't yet grasp. What's even stranger is how these storms feed themselves. Once unleashed, the Great White Spot behaves like a self-sustaining monster. The initial updraft punches through the upper atmosphere, dragging warmer gas from below that fuels further convection. This creates a runaway effect, with the storm scooping up energy like a hurricane on steroids. Towering thunderheads shoot 25 miles high, 10 times taller than Earth's mightiest storms, while lightning bolts 1,000 times more powerful than ours crackle through the ammonia-laced clouds. Yet the biggest mystery is what happens beneath the chaos. Radio emissions detected during these events hint at deep atmospheric disruptions, as if the storm is dredging up material from layers usually hidden from view. Some theories suggest reservoirs of water vapor, normally locked far below, might be thrust upward, freezing into the bright white ammonia crystals that give the storm its name. Others propose these megastorms might be Saturn's way of balancing heat, like a planetary pressure valve finally blowing. What makes the Great White Spot so captivating isn't just its fury, it's the glimpse it offers into gas giants everywhere. If we can decode why Saturn's storms march to such a predictable beat, we might finally understand the hidden rhythms of distant exoplanets, where seasons last centuries and storms might rage for lifetimes. For now, though, this tempest remains a humbling reminder. Even in a silent vacuum, nature knows how to scream. In the outer edges of Saturn's a ring, where icy particles jostle like cars in celestial traffic, astronomers witnessed something bizarre in 2013, a blip in the data, a tiny disturbance that shouldn't have been there. Dubbed Peggy, this strange anomaly appeared to be a moon in the act of being born or perhaps dying. For a brief moment, NASA Cassini spacecraft captured what looked like a fledgling moonlet, no bigger than half a mile across, nestled within the rings. Then, just as suddenly as it appeared, Peggy began to unravel, its signature fading like a shadow dissolving in sunlight. Was this a moon caught in the act of formation, or a fragile victim of Saturn's relentless gravity? The answer might rewrite what we know about how moons are made and unmade. What made Peggy so tantalizing was its location. Saturn's rings aren't just static bands of ice. They're dynamic nurseries where particles collide, clump, and sometimes snowball into larger bodies. Peggy's position near the outer edge of the ring, where material is densely packed, suggested it could be a moon in its earliest stages. A rare glimpse of a process thought to have shaped Saturn's smaller moons like Pan and Daphne's. These so-called shepherd moons grow by sweeping up ring material, their gravity carving gaps in the rings as they go. Peggy might have been the next in line, a proto-moon caught mid-assembly. But there's another, darker possibility. Saturn's gravity is a ruthless sculptor, and the region where Peggy appeared sits perilously close to the Roche limit, the point where tidal forces overwhelm a moon's own gravity, tearing it apart. Some researchers argue Peggy wasn't being born at all, but instead suffering a violent death. As it ventured too close to Saturn, the planet's pull could have stretched and fractured it, scattering debris back into the rings like crumbs tumbling from a broken loaf. This would explain why Peggy's signal dimmed over time, as if the moonlet was dissolving before Cassini's eyes. The real mystery lies in Peggy's structure. Was it a solid body, or just a loose cluster of ice held together by fleeting gravitational bonds? If it was a true moonlet, its disintegration challenges our models of moon formation, suggesting even fully formed satellites can be shredded by Saturn's tides. If it was merely a transient clump, it reveals how chaotic and fertile the rings truly are, with temporary structures flaring up and vanishing like cosmic mayflies. Either way, Peggy's fleeting existence forces us to confront a haunting idea. We might be witnessing Saturn's rings in their death throes, recycling material into doomed moons that never fully form. Or perhaps Peggy was a rare survivor, a moonlet that briefly escaped the grind of orbital mechanics before being dragged back into the chaos. Until another Peggy-like anomaly appears, this enigmatic blip remains a ghost in the data, a whisper of the violent, ever-changing ballet playing out in Saturn's rings. Deep in the electromagnetic buzz of Saturn's polar skies, a ghostly chorus echoes across space, bursts of radio waves so powerful they'd deafen human ears if sound could travel through the void. This is Saturn kilometric radiation, or SKR, a haunting emission that crackles at frequencies hundreds of times higher than Earth's aural radio signals. But what makes these transmissions truly alien isn't just their pitch, it's their bizarre synchronization with Saturn's rotation, a rhythm so precise it once fooled scientists into misjudging the planet's day. Unlike Jupiter's steady, clockwork radio pulses, Saturn's SKR stutters and shifts like a broken record. For decades, researchers assumed these emissions, generated by charged particles spiraling along magnetic field lines, would reveal Saturn's true rotation rate, the heartbeat of its hidden interior. Yet when Cassini measured them, the data unraveled into chaos. The radio bursts didn't match a single rotation period. Instead, they split into multiple frequencies, with northern and southern hemispheres blaring slightly out of sync, as if the planet couldn't decide on its own rhythm. The plot thickened when scientists realized these radio voices weren't just discordant, they migrated over time. Between 2004 and 2009, the northern SKR signals slowed by about 1%, while the southern emissions sped up by an equal amount. Then, around 2010, something extraordinary happened. The hemispheres swapped tempos. It's as if Saturn's magnetic field is caught in a tug of war between its poles, with each side occasionally stealing the lead. What could possibly cause such electromagnetic anarchy? One theory points to water. Unlike Jupiter, where radio emissions are driven by volcanic Eo's sulfur dioxide, Saturn's signals may be linked to geysers erupting from Enceladus. As these water molecules ionize, they could load Saturn's magnetic field with extra mass, altering how it couples to the planet's deep interior. Others suggest the answer lies in Saturn's seasons. As sunlight shifts over its 30-year orbit, it might unevenly heat the upper atmosphere, distorting the magnetic field's shape like a finger pressing on a guitar string. The most tantalizing clue came from Cassini's grand finale orbits, which dove between Saturn and its innermost ring. These risky maneuvers revealed the planet's magnetic field is tilted less than 0.06 degrees, nearly perfectly aligned with its spin axis. That shouldn't happen. Planetary magnetic fields usually tilt enough to wobble visibly, like Earth's 11-degree offset. This near-perfect alignment suggests something deep inside Saturn. Perhaps a layer of helium rain or metallic hydrogen is smoothing out the kinks, masking the true rotation rate that SKR once seemed to promise. These radio emissions aren't just cosmic static, they're a cipher. Every erratic pulse, every hemispheric duel carries encrypted details about Saturn's interior structure, atmospheric winds, and even its enigmatic core. Untangling their patterns might finally answer why this gas giant dances to such an odd electromagnetic beat while its siblings march in time. Until then, Saturn's kilometric whispers remain a siren song for scientists, a reminder that even the loudest signals in space can guard their secrets fiercely. On Saturn's largest moon, Titan, it rains. Rivers carve valleys into icy bedrock, waves lap against shorelines, and storms brew in thick, soupy clouds, yet this isn't the water-driven world we know. Titan's hydrologic cycle runs on methane, a liquid that behaves like water here but under conditions so alien, it transforms the moon into a funhouse mirror of Earth. At -290 degrees Fahrenheit, methane takes on roles we'd recognize instantly. It fills lakes as deep as the Great Lakes, evaporates into smoggy skies, and condenses back into rain that darkens the dunes below. But the sheer scale of this methane cycle defies logic. Titan's rivers should have evaporated away eons ago, its lakes drained by chemical reactions. So why does this moon still slosh with hydrocarbons, and where is all that methane coming from? The parallels to Earth's water cycle are uncanny and deceptive. Titan's clouds drizzle methane for years, not hours, with storm systems so sluggish. A single downpour might last for decades. When Cassini's radar pierced the moon's haze, it revealed landscapes sculpted by lazy, branching rivers that meander like the Mississippi, yet flow 1,000 times slower. These rivers empty into vast polar seas. Kraken Mare alone spans larger than the Caspian, where methane mixes with ethane and propane into a cocktail that would fuel rockets on Earth. Even the shorelines mimic terrestrial features, with tides driven not by Saturn's gravity but by atmospheric pressure changes, creating waves that inch forward like slow-motion breakers. But here's the puzzle. Sunlight should have destroyed Titan's methane long ago. Ultraviolet radiation breaks methane molecules apart, converting them into heavier hydrocarbons like ethane that rain down and accumulate. Models suggest Titan's entire methane inventory, enough to cover the moon in a 3,000-foot-deep ocean, should have vanished within 50 million years. Yet Titan's lakes are full, its rivers active, as if someone keeps refilling the tank. The moon's thick nitrogen atmosphere, which ought to be methane-starved by now, still holds a steady 5% concentration of the gas, like a car idling forever on fumes. One theory points to a hidden methane vault deep underground. Cryovolcanoes might periodically belch fresh methane into the atmosphere, replenishing what's lost to photochemistry. Cassini spotted candidate volcanic features, dome-like rises with flow patterns but no smoking guns. Another idea involves a subsurface reservoir of liquid methane, trapped between layers of ice like an aquifer, slowly seeping through fractures. The most tantalizing and controversial hypothesis, microbial life. Certain methane-eating bacteria on Earth thrive in oxygen-free environments, and Titan's methane could be waste from organisms metabolizing hydrogen and acetylene. It's a long shot, but not impossible. Then there's the wild card. Titan's chemistry might be recycling methane in ways we haven't imagined. Ethane ice sinking into warmer subsurface layers could theoretically break down back into methane, creating a closed-loop system. Or perhaps impacts from comets periodically deliver fresh methane, like cosmic gas stations. Every explanation has holes, leaving scientists to wonder if Titan's entire surface is just the visible tip of a hydrocarbon machine operating on geological timescales. What makes Titan's methane cycle so mesmerizing isn't just its strangeness, it's the reminder that nature repurposes familiar scripts under alien conditions. Here, methane plays every role water does on Earth: solvent, landscape sculptor, even potential enabler of life. And as we puzzle over its origins, we're forced to reconsider what it means for a world to be Earth-like at all. Titan's rivers may not be wet, but they're writing the same story in a different language, one we're only beginning to decode. One of Titan's greatest sleights of hand is happening right now on the glassy surface of Ligeia Mare, its second largest sea. In 2013, Cassini's radar captured something impossible: a bright, mile-sized splotch that hadn't been there before, lounging in the methane waves like an uninvited guest. Scientists dubbed it the Magic Island, not for any supernatural quality, but because by 2014 it had vanished without a trace. Then, in 2016, it reappeared, only to fade again, as if Titan itself was playing a cosmic game of peek-a-boo. What makes this phantom feature so baffling isn't just its disappearing act, it's the challenge of explaining what could possibly float, froth, or freeze in these alien waters. Ligeia Mare isn't filled with water. It's a frigid bath of methane and ethane, with temperatures so low that any earthly iceberg would sink like a stone. Yet something is breaking the surface here, and the leading theories read like a mad scientist's brainstorm. The first contender: waves. Real, rolling waves, something scientists once thought impossible on Titan, given its thick atmosphere's damping effect. But Cassini spotted sunlight glinting off Ligeia's surface, hinting at disturbances. If winds occasionally whip up sizable swells, they might reflect radar brightly enough to mimic land. Then there's the bubble hypothesis. Like a soda bottle shaken then opened, Titan's seas could be fizzing with nitrogen or methane gas. Seasonal temperature shifts might release dissolved gases in explosive bursts, creating transient foamy patches that vanish when the bubbles pop. Supporting this idea are Cassini's observations of phantom lakes, small depressions along shorelines that fill and drain over years, possibly from subsurface gas pushing liquid around like a lazy subterranean fountain. But the wildest explanation involves something never seen beyond Earth: icebergs, not water ice, which would be denser than Titan's hydrocarbon soup, but frozen chunks of wax-like compounds. At Ligeia's temperatures, acetylene and benzene, normally gases or powders on Earth, could solidify into buoyant, porous clumps. These organic icebergs might detach from the seabed during seasonal changes, float briefly, then melt or sink as conditions shift. Some models even suggest they could trap pockets of gas, making them pop up and down like submerged buoys. The Magic Island's erratic behavior adds another wrinkle. Unlike predictable earthly phenomena, it doesn't follow a schedule. Its appearances align roughly with Titan's northern summer, when increased sunlight might trigger winds or gas release, but the timing is inconsistent. This has led to fringe theories, including transient tidal forces from Saturn flexing the moon's crust or even floating mats of microbial life, though that's purely speculative. What's clear is that Ligeia Mare isn't the stagnant pool we once imagined. It's dynamic, chaotic, and still full of surprises. Every flicker of the Magic Island forces us to rethink how liquids behave under alien skies, and whether similar mysteries might ripple across the hydrocarbon seas of exoplanets light years away. Until we land a boat on Titan's shores, this vanishing act will remain one of the solar system's most captivating enigmas, a puzzle written in methane and sung by an ever-changing tide. Saturn's second largest moon, hides a secret so delicate you could walk right through it without noticing: an atmosphere. Not the thick, soupy haze of Titan, but a whisper-thin veil of oxygen and carbon dioxide, so tenuous it makes Earth's stratosphere feel dense by comparison. This wasn't just any discovery. When NASA Cassini spacecraft detected it in 2010, became the first moon ever found with an oxygen atmosphere, rewriting the playbook on how celestial bodies hold onto gases in the void of space. What makes Rhee's air so baffling isn't just its existence, it's the source. Unlike Earth, where plants and algae pump out oxygen, Rhee's supply comes from pure violence. High-energy particles from Saturn's magnetic field slam into the Moon's icy surface, blasting water molecules apart like microscopic grenades. The hydrogen atoms escape into space, while the heavier oxygen atoms cling just long enough to form a fleeting atmosphere. It's a process called radiolysis, and it's happening in slow motion across Rhee's frozen plains, turning the Moon into a cosmic chemistry set. But here's the twist: Rhee shouldn't be able to hold onto this oxygen at all. With gravity only 1/35th as strong as Earth's, molecules should zip away instantly. Yet Cassini found oxygen densities up to 100 trillion molecules per cubic meter, far higher than expected. The answer might lie in Rhee's chaotic surface. Fresh ice exposed by impacts or tectonic shifts could provide a continuous supply of material for radiation to split, while the Moon's own weak gravity and Saturn's magnetic field might create temporary traps where gases pool like puddles after a rainstorm. Even stranger is the carbon dioxide mixed into Rhee's air. Unlike oxygen, which forms from surface ice, carbon dioxide requires carbon sources, something scarce on an iceball moon. Some scientists speculate it's primordial, locked in Rhee's interior since the solar system's birth and slowly seeping out through cracks. Others propose a more dynamic origin, cosmic rays transforming carbon-rich dust delivered by meteorites into gas. Either way, this carbon dioxide is vanishing almost as fast as it appears, suggesting Rhee's atmosphere is less a stable layer and more a flickering hologram, appearing and disappearing with every particle bombardment. What makes this discovery groundbreaking isn't just the oxygen, it's the implication. If a frigid, airless moon like Rhee can temporarily host Earth-like gases through pure physics, then countless icy worlds across the galaxy might do the same. Suddenly, moons orbiting Jupiter, Uranus, or even exoplanets become candidates for rudimentary atmospheres, no biology required. Rhee's ghostly breath challenges us to rethink how dead worlds might still pulse with activity, however faint. And as we stare out into the cosmos, it begs the question, how many other invisible atmospheres are we missing, hiding in plain sight? Among Saturn's many icy moons, Dione wears its scars like ethereal lace, bright, wispy streaks stretching across its surface like brushstrokes on a frozen canvas. These ghostly fractures, some over 60 miles long, gleam against the moon's darker plains, as if someone dragged a chisel through its crust and filled the wounds with light. For years, scientists dismissed them as surface cracks frozen in time. But when NASA Cassini spacecraft swooped in for a closer look, it revealed something astonishing. These aren't mere scratches. They're towering cliffs of ice, some soaring hundreds of feet high, their sheer faces reflecting sunlight like celestial mirrors. The story etched into these cliffs is one of cosmic violence. Dione's wispy terrain likely formed billions of years ago, when the moon's interior was still warm enough to flex under Saturn's gravitational pull. As tidal forces stretched and compressed its icy shell, titanic faults ruptured, thrusting slabs of pristine ice upward like frozen tectonic sails. Over time, debris sliding down their slopes darkened the surrounding terrain, leaving the cliffs themselves stark and bright, a geological negative of shadow and light. But here's the twist: similar fractures on other moons, like Enceladus, often hint at hidden oceans. Could Dione's scars be whispering the same secret? Beneath its icy crust, Dione might harbor a liquid ocean of its own, a buried sea kept warm by the same gravitational kneading that sculpted its surface. Cassini's gravity measurements revealed anomalies suggesting a dense, sloshing layer beneath Dione's ice, possibly water laced with ammonia or salts to keep it liquid. Even more compelling, the moon's faint oxygen atmosphere detected by Cassini mirrors Rhee's, hinting at radiolysis splitting water molecules seeping from below. But unlike Enceladus with its dramatic geysers, Dione's ocean would be locked under miles of ice. its existence betrayed only by subtle cracks and chemical whispers. The real mystery lies in Dione's silence. If it has an ocean, why no plumes? One theory suggests its ice shell is simply too thick for water to erupt through. Another proposes that Dione's ocean is transient, a relic of past tidal heating that's slowly freezing solid, leaving only these cliffs as tombstones to its former vitality. Or perhaps we've just missed the eruptions. Cassini spotted odd, faint particle streams near Dione, too sparse to be geysers but too regular to ignore. What makes Dione's wispy streaks so haunting isn't just their beauty, it's the duality they represent. These gleaming cliffs could be monuments to a dead, frozen world or windows into yet another hidden ocean, waiting patiently to be discovered. As we study their reflective faces, we're left to wonder, is Dione a frozen fossil or a dormant giant with secrets still stirring beneath its ice? The answer might rewrite what we know about how common life's hiding places truly are. Saturn's magnetic field should be a mess. Like most planets with active dynamos, its magnetic poles ought to tilt significantly compared to its axis of rotation. Just look at Earth's 11-degree offset or Uranus's bizarre 59-degree skew. Yet Saturn defies the odds with a magnetic alignment so precise, it's almost eerie. Measurements from Cassini's final orbits revealed a tilt of less than 0.06 degrees, so minuscule. It's as if someone balanced the planet's entire magnetic field on a razor's edge. This near-perfect symmetry isn't just unusual, it's downright suspicious, leaving scientists scrambling to explain how a gas giant spinning at 22,000 miles per hour manages such impeccable alignment. The mystery deepens when you consider how planetary magnetic fields form. These invisible shields arise from churning, electrically conductive fluids deep inside a planet: molten iron for Earth, metallic hydrogen for Saturn. Turbulent and chaotic, these dynamos almost never produce fields perfectly aligned with rotation. Jupiter's tilt 9.6 degrees, Neptune's 47. Even the Sun's magnetic axis drifts, so why is Saturn's field so unnervingly straight? One radical theory suggests the answer lies in helium rain, deep within Saturn's interior, where pressures crush hydrogen into a metallic soup. Helium might condense into droplets and rain downward through lighter layers. This relentless downpour could act like a cosmic stabilizer, smoothing out kinks in the magnetic field like weights on a spinning top. Another possibility involves Saturn's hidden oceans. Just as saltwater conducts electricity on Earth, a layer of ionized water deep beneath Saturn's clouds might be redistributing magnetic energy, effectively ironing out wrinkles in the field. Some models even propose that Saturn's magnetic dynamo operates in an unusually thin shell, sandwiched between stable layers that suppress tilting forces. But every explanation hits a snag. If the field is so perfectly aligned, why does Saturn's kilometric radiation, those ghostly radio emissions, wobble so unpredictably? The signals, once thought to mirror the planet's rotation, dance between hemispheres like a broken metronome, utterly at odds with the field's pristine geometry. Perhaps the most tantalizing clue came from Cassini's death dive. As the probe plummeted into Saturn's atmosphere, it detected subtle magnetic fluctuations suggesting the field might actually be slowly tilting, just too sluggishly for us to notice over short observations. Imagine a gyroscope gradually losing balance over millennia. If true, we might be witnessing Saturn at a rare moment of near-perfect alignment, a cosmic coincidence frozen in time. Whatever the reason, this magnetic enigma forces us to rethink how dynamos work. If Saturn can maintain such symmetry amid its turbulent depths, what other impossible alignments might exist in the universe? The answer could rewrite not just our understanding of gas giants, but the very physics shaping worlds light years away. Beyond Saturn's dazzling main rings, hidden in the inky blackness, lies a ghostly halo so vast it defies comprehension, the Phoebe ring. Discovered in 2009 by NASA's Spitzer Space Telescope, this faint band of dust stretches over 7.5 million miles from Saturn, far enough to swallow 20 full moons lined up side by side. But what makes this ring truly bizarre isn't just its size, it's the way it dances to its own rhythm, tilting 27 degrees off Saturn's equatorial plane and spinning backward against the flow of nearly every other ring and moon in the system. This isn't just debris, it's a cosmic crime scene, and the prime suspect is Saturn's dark, irregular moon Phoebe, a celestial vagabond that might hold the key to one of the solar system's strangest rings. Phoebe itself is an oddball, a captured moon, likely a refugee from the Kuiper belt, orbiting Saturn in the opposite direction of its larger siblings. Roughly spherical and coated in pitch-black material, it's pockmarked with craters that tell a violent history. When micrometeorites slam into Phoebe's surface, they kick up dust particles that escape its weak gravity, sending them spiraling into space. Over eons, these particles, dark as charcoal and fine as smoke, have formed a colossal debris field, shepherded by Saturn's gravity into a sprawling, lopsided torus. Unlike the icy brilliance of Saturn's main rings, the Phoebe ring is a shadowy realm, absorbing sunlight rather than reflecting it, which explains why it eluded detection for so long. But here's the twist: this ring shouldn't be stable. Solar radiation and planetary magnetic fields should have scattered Phoebe's dust long ago. The fact that it persists suggests a constant supply of fresh material, as if Phoebe is hemorrhaging dust faster than physics predicts. Some researchers speculate that Phoebe's surface is unusually fragile, perhaps rich in volatile ices that sublimate when exposed to sunlight, loosening particles like a dry sandstone cliff crumbling in the wind. Others propose that larger impacts, collisions with stray asteroids, periodically blast massive clouds of debris into orbit, replenishing the ring in sudden, violent bursts. The Phoebe ring isn't just a curiosity, it's a silent disruptor. Its backward spinning particles likely bombard Saturn's other moons, particularly Iapetus, whose two-faced appearance, one hemisphere black, the other white, might be the result of this dark rain. As Phoebe's debris drifts inward, it smears across Iapetus's leading face like paint on a windshield, creating the stark contrast we see today. This makes the ring a celestial middleman, connecting distant Phoebe to moons far closer to Saturn in a gravitational game of cosmic billiards. What's most haunting about the Phoebe ring, though, is what it represents: a fossil record of destruction. Every speck of dust carries a fragment of Phoebe's history, a story of collisions, captures, and slow disintegration written in particles too small to see. And as we study this faint halo, we're left to wonder how many other invisible rings, woven from the debris of forgotten moons, might linger in the darkness waiting to be discovered. Of all Saturn's moons, none wears its origin story quite like Pan, a celestial oddity that looks less like a moon and more like a walnut someone stepped on. This tiny world, barely 17 miles across, sports a ridge so pronounced it gives Pan the appearance of a flying saucer, or, as some cheekily call it, cosmic ravioli. But this isn't just a whimsical shape. It's a fossil record of Pan's violent past, written in the very ring material it spent eons devouring. Pan's story begins in the chaotic ballet of Saturn's rings, specifically within the Inca Gap, a 200-mile-wide clearing in the ring where this moon reigns as shepherd. As Pan orbits, its gravity sculpts the gap's edges, carving out precise waves in the icy particles like a boat plowing through water. But over millions of years, those same particles have been returning the favor, raining down onto Pan's equator and piling up into that bizarre ridge. Imagine a snowball rolling downhill, gathering layer after layer until it's less a sphere and more a squashed disk. That's Pan in a nutshell, a moon shaped by its own appetite. The physics behind this accretion is just as fascinating as the result. Pan's weak gravity, about 1/10,000th of Earth's, creates a strange environment where ring particles don't just collide and stick, they practically float onto the surface. Simulations suggest the ridge grew from material sliding lazily down Pan's slopes, drawn by gravity's whisper-thin pull, accumulating into a belt that now towers up to 2 miles high in places. What's wild is that this ridge isn't static, it's still growing with fresh ring dust settling onto it like cosmic dandruff. But why does the ridge stay put? Pan's rapid rotation, one full spin every 13 hours, should fling loose material back into space. Yet the ridge holds firm, suggesting the particles sinter together, fusing into a solid, porous crust. Some scientists compare it to fairy castle structures in Earth's deserts, where grains bond into fragile but cohesive shapes. This delicate balance between accumulation and erosion means Pan's ridge is a snapshot of an ongoing process, a work in progress written in ice and time. The real kicker: Pan might not be alone. Other small moons like Atlas and Daphne sport similar equatorial bulges, hinting that this is a common fate for shepherds grazing Saturn's rings. These cosmic oddballs challenge our notion of what a moon should look like, proving that gravity and patience can sculpt worlds into shapes no artist would dare imagine. As we study Pan's ridges, we're not just seeing a moon, we're witnessing the slow-motion art of orbital mechanics, where even the smallest actors leave their mark on the grandest stages. If Pan resembles a cosmic ravioli, then its sibling Atlas is more like a flying dinner plate, a moon so improbably thin, it seems to defy the laws of planetary formation. This 16-mile-wide oddball, another of Saturn's inner shepherds, sports an equatorial ridge so extreme it accounts for nearly a third of the moon's total volume, flaring outward like the brim of a hat. But while Pan's ridge looks sculpted by time, Atlas's appears almost engineered, with edges so sharp they cast knife-like shadows across its surface. What forces could mold ice into such a precise, unnatural shape? The answer lies in the silent feeding frenzy happening right now in Saturn's rings. Atlas orbits just beyond the ring's outer edge, where it plays gravitational gatekeeper to a reservoir of icy particles. Every pass it makes sends ripples through the ring material, herding stray bits like a celestial sheepdog. But the rings aren't passive victims, they're returning the favor. As particles drift toward Atlas's equator, drawn by its minuscule gravity, they stick not just through simple collisions but through an exotic process called electrostatic accretion. In the vacuum of space, where temperatures hover near absolute zero, ice grains become statically charged, clinging together like microscopic magnets. This isn't the slow buildup of a snowball, it's more like Velcro on a cosmic scale, with particles snapping into place along Atlas's midline, building that impossible ridge grain by grain. The real puzzle is why Atlas's ridge is so much more pronounced than Pan's. One clue comes from their orbits. Atlas skims the ring's edge, where particle density is far higher than in Pan's Keg Gap. More debris means faster accretion, potentially explaining Atlas's dramatic flared profile. There's also the question of composition. Cassini's measurements revealed Atlas's ridge is far brighter than its core, suggesting it's made of fresher, less contaminated ice, material recently plucked from the rings and not yet darkened by eons of radiation. It's as if we're watching the ridge form in real time, a live demonstration of moon-building physics. Yet even this explanation has cracks. Some models predict Atlas's rapid spin, it completes a rotation every 5 hours, should fling loose material off its equator, not trap it. This suggests something stranger is at work. The ridge might be held together by forces stronger than gravity or static. Ice at these temperatures can sinter into a porous but cohesive foam, creating a structure light enough to resist centrifugal forces but strong enough to maintain its shape. Imagine a fragile coral reef growing underwater, except here the water is the vacuum of space, and the coral is hypercold ice fusing at a molecular level. Atlas's ridge isn't just a geological quirk, it's a window into how all moons might have begun. In the early solar system, before planets cleared their orbits, countless tiny worlds likely grew this way, skimming material from protoplanetary disks. By studying Atlas, we're glimpsing the infancy of cosmic construction, watching as physics sculpts a moon before our eyes. And as it continues its endless feast on Saturn's rings, we're left to wonder, will its ridge keep growing until the moon resembles a spinning top, or will some unseen limit finally put a cap on this celestial binge-eating? For now, Atlas remains both artifact and artist, a moon shaped by the very debris it was meant to control. Saturn's moon Tethys carries a scar so vast it defies belief, a crater named Odysseus, stretching 280 miles wide, nearly half the moon's entire diameter. To put that in perspective, if Earth bore a crater proportionally this size, it would span from New York to Chicago, a gaping wound visible from space. Most objects hit this hard would shatter like glass, yet Tethys survived, its icy body bearing this ancient impact like a cosmic badge of resilience. How could a moon endure such violence without disintegrating? The answer lies in the strange, almost rubbery nature of Tethys's frozen interior, and a delicate dance between destruction and gravity. When Odysseus struck billions of years ago, Tethys was likely warmer and more malleable, its ice laced with ammonia or other antifreeze compounds that kept it slightly soft. Instead of fracturing like brittle glass, the moon's surface may have absorbed the blow like a slow-motion punch to dough, with the crater's edges sagging inward over time. This viscous relaxation, a gradual flow of ice under its own weight, smoothed Odysseus's once jagged rim into the gentle bowl we see today, disguising the true violence of its origin. Even the crater's floor sits nearly 2 miles below Tethys's surface level, not because the impact gouged that deep, but because the moon's viscoelastic ice slowly rebounded upward like memory foam after a weight is lifted. But survival came at a cost. Odysseus's sheer size warped Tethys's very shape. The moon isn't a perfect sphere, it bulges slightly toward the crater, as if still recoiling from the blow. Gravity measurements from Cassini revealed anomalies in Tethys's mass distribution, hinting that the impact may have redistributed material deep beneath the surface, leaving the moon forever unbalanced. Yet despite this trauma, Tethys's icy shell shows no signs of global cracking, suggesting its interior absorbed the shock like a cosmic shock absorber. The real mystery isn't just how Tethys survived, it's what Odysseus exposed. The crater's central peaks, towering over 12 miles high, gleam brighter than the surrounding terrain in spectrometer data. This suggests the impact blasted through darker surface layers, revealing purer ice from Tethys's subsurface. Some scientists speculate these bright patches could be water ice laced with organic compounds, flash frozen during the collision and preserved in the vacuum of space. If true, Odysseus isn't just a scar. It's a window into the moon's primordial composition, a snapshot of the ingredients that built Saturn's icy satellites. What makes this crater extraordinary isn't its size alone, but the questions it raises about survival in the cosmos. If a moon as small as Tethys, barely 600 miles across, can withstand an impact that should have destroyed it, what other impossible feats of cosmic endurance might we be missing? Odysseus stands as a testament to the universe's capacity for violence and resilience in equal measure, a reminder that even the deepest wounds can become landmarks given enough time. And as we study its smoothed edges and gleaming peaks, we're left to wonder, how many other battered worlds wear their histories not as fractures but as quiet badges of perseverance? Mimas doesn't just resemble the Death Star, it puts the sci-fi icon to shame. One colossal crater, Herschel, dominates this moon's face like a bullseye, its central peak jutting 4 miles high from a basin deep enough to swallow Mount Everest. The impact that carved this nightmare was so violent, it should have shattered Mimas into a million icy fragments. Yet here it hangs, a cracked but unbroken testament to the chaos of Saturn's early days, leaving scientists to wonder, How does a moon made mostly of water ice survive a blow that would vaporize solid rock? The numbers behind Herschel's formation read like a disaster movie. The asteroid or comet that struck Mimas was likely over 5 miles wide, hitting at speeds surpassing 12 miles per second. The energy released would have been equivalent to detonating 1,000,000 nuclear bombs simultaneously, melting ice across half the moon's surface and sending shockwaves rippling through its core. What's miraculous isn't the crater's size, though at 81 miles wide, it spans a third of Mimas's diameter, but the fact that the moon didn't disintegrate into Saturn's rings. Cracks radiating from Herschel's opposite side hint at the strain, as if Mimas was literally holding itself together by a thread. Survival came down to two unlikely factors: timing and temperature. When Herschel formed over 4 billion years ago, Mimas was likely still warm from its own accretion, its icy crust more pliable than today's frozen shell. Instead of shattering like a dropped ice cube, the moon may have absorbed the impact's energy like a sponge, its interior deforming slowly enough to prevent total fragmentation. Some models suggest Mimas even had a subsurface ocean back then, a slushy buffer beneath the ice that dissipated the shockwaves before they could ripple catastrophically around the moon. But the real mystery lies in Herschel's uncanny resemblance to a certain sci-fi superweapon. The crater's central peak, a jagged spire formed when the impact's recoil snapped material upward like a rubber band, mirrors the Death Star's laser emitter almost perfectly. It's a coincidence so striking, even NASA couldn't resist referencing it when releasing Cassini's images. Yet this peak holds real scientific value. Its height and shape reveal clues about Mimas's internal structure. The way it settled after the impact suggests the moon's icy crust floats atop a denser, partially differentiated interior, like a frozen lake over mud. Herschel's aftermath raises even thornier questions. Why doesn't Mimas show signs of resurfacing like Enceladus or Dione? Its ancient, battered face suggests geologic inactivity for eons, yet Cassini detected odd thermal anomalies around the crater, pockets of warmer ice that defy expectations for such a frigid world. Some researchers speculate latent heat from the impact might still linger, trapped beneath an insulating layer of porous ice. Others argue these warm spots could hint at residual tidal flexing, a ghost of the forces that once kept Mimas malleable. What makes Herschel more than just a cosmic curiosity is its window into planetary extremes. This crater straddles the line between destruction and survival, a case study in how icy bodies endure trauma that would obliterate rocky ones. As we study its fractured edges and towering peak, we're glimpsing the violence that shaped not just Saturn's moons, but the entire solar system. And somewhere in those icy scars lies a deeper truth. Sometimes the most enduring worlds are the ones that came closest to breaking. Saturn's poles don't just shimmer, they ignite with curtains of light so immense they could wrap around Earth twice over. These aren't your typical northern lights, they're auroras on cosmic steroids, blazing in hues our eyes can't even see. While Earth's auroras paint the sky in shimmering greens and pinks, Saturn's dance in ultraviolet and infrared, invisible without special instruments but radiating enough energy to power civilizations. What fuels this otherworldly light show? A perfect storm of solar fury and planetary magnetism, with twists that make our planet's displays look quaint by comparison. The mechanics start familiarly enough. Charged particles from the solar wind, funneled by Saturn's magnetic field, slam into its upper atmosphere, but here's where the similarity ends. Earth's magnetic field is like a cozy blanket, relatively tight and symmetrical. Saturn's, by contrast, is a sprawling, messy force. Its magnetic field lines stretch so far, they sometimes snap like rubber bands, catapulting particles at speeds that supercharge the auroras. These particles collide with hydrogen molecules unlike Earth's oxygen and nitrogen, and that's where the magic happens. Hydrogen excites at wavelengths our eyes can't detect, glowing fiercely in ultraviolet when energized and pulsing in infrared as it cools. The result, a light show that's less about color and more about raw, radiant power. Timing plays a role too. Saturn's auroras don't just flicker in response to solar storms, they pulse to their own rhythm, flaring bright every Saturnian day about 10.5 Earth hours. Scientists suspect this heartbeat is tied to the planet's bizarre magnetic field alignment, where internal forces and solar wind compete to conduct this electromagnetic symphony. And then there's the sheer scale. While Earth's auroras cling to polar ovals, Saturn's can sprawl across thousands of miles, towering up to 800 miles high, so vast Cassini once observed them stretching halfway to the equator. But the real kicker, Saturn's auroras sometimes blaze without the solar winds prompting. Hubble and Cassini spotted eruptions fueled by Enceladus as geyser particles ionize and hitch rides on magnetic field lines. This means Saturn's light shows aren't just solar-powered, they're hybrid performances, with moons and rings pitching in like celestial collaborators. What makes these auroras more than just eye candy is what they reveal about Saturn's hidden machinations. Their infrared glow hints at temperatures in the upper atmosphere soaring to 1100 degrees Fahrenheit hotter than Venus, defying models of gas giant thermodynamics. And their ultraviolet pulses trace the invisible contours of Saturn's magnetic field, mapping its quirks better than any probe could. Every flicker is a Morse code from the planet's depths, a luminous clue to forces we're only beginning to decode. So while we might never see these auroras with our own eyes, their unseen radiance holds the keys to understanding a world where even light plays by different rules. Titan's methane cycle should have left the moon drowning in ethane, a thick, gloopy sludge covering its surface from pole to pole. Every time sunlight splits methane molecules in Titan's atmosphere, the fragments recombine into heavier hydrocarbons, with ethane being the most abundant byproduct. Over billions of years, this chemical snowfall should have accumulated into deposits hundreds of meters deep, enough to blanket entire continents. Yet when Cassini surveyed Titan's lakes and seas, it found mostly methane with barely a tenth of the expected ethane. So where did it all go? One possibility is hiding in plain sight. Titan's hidden underground vaults. Ethane, unlike methane, doesn't evaporate easily at Titan's frigid temperatures. Instead, it could seep into the moon's porous ice crust like water soaking into a sponge, pooling in subterranean reservoirs far below the surface. Cassini's radar spotted areas where the ground appears unusually reflective, hinting at smooth, possibly liquid-filled caverns. If ethane has been draining into these icy aquifers for eons, it might explain the shortage on the surface. Some models suggest cryovolcanoes could even erupt this sludge back into the atmosphere, creating temporary ethane clouds before the molecules break down further into even heavier compounds. Then there's the ocean theory. Titan's subsurface ocean, a salty, ammonia-rich body of water sloshing beneath the ice, might be dissolving ethane like sugar in tea. Lab experiments show ethane readily mixes with ammonia water solutions, especially under high pressure. If cracks in the ice allow surface hydrocarbons to percolate downward, Titan's ocean could be hoarding ethane in concentrations we've yet to measure. This would make the ocean not just a potential haven for life, but a cosmic hiding spot for missing chemicals. But the wildest idea, Titan might be burning its ethane. Not with fire, of course. There's no oxygen, but through chemical reactions with minerals like olivine. On Earth, similar processes create methane hydrates. On Titan, the reverse could happen, with ethane reacting to form more complex polymers or even sinking into clathrate cages in the ice. Cassini detected benzene and other heavy hydrocarbons in Titan's haze, suggesting ethane might be getting cooked into these longer chains, effectively disappearing from the inventory. The real twist is that all these explanations could be true simultaneously. Ethane might be hiding underground, dissolving into oceans, and transforming into new molecules, a triple vanishing act spanning geology, chemistry, and atmospheric science. Every unaccounted molecule is a clue to Titan's deeper mysteries, how its surface renews itself, how its interior interacts with its lakes, and whether its chemistry could be more dynamic than we ever imagined. Until we land a probe capable of tasting Titan's depths, this missing ethane will remain a phantom, a reminder that even the most careful calculations can't always predict what a world like Titan will do next. Saturn's upper atmosphere shouldn't be this hot. By all rights, the sunlight reaching this distant giant is too feeble to explain temperatures soaring over 1100 degrees Fahrenheit hotter than the surface of Venus. Yet there it is, a thermal paradox glowing against the cold void of space, leaving scientists scrambling to find the hidden furnace behind this unexpected warmth. Earth's upper atmosphere sizzles because it absorbs ultraviolet radiation, but Saturn's heat signature is too extreme for solar input alone. So what's cooking this gas giant's outer layers? The answer might lie in forces more dynamic than sunlight, a celestial energy transfer so efficient it rewrites our understanding of planetary climates. One leading suspect, Saturn's auroras. These colossal light shows aren't just pretty, they're power plants. As charged particles spiral along magnetic field lines and collide with atmospheric hydrogen, they don't just produce light, they dump staggering amounts of energy into the upper atmosphere. Think of it like a cosmic microwave where magnetic turbulence heats gas molecules to breaking point. But here's the catch: auroral heating is localized around the poles. Saturn's warmth, however, blankets the entire upper atmosphere, suggesting some unseen conveyor belt must be redistributing that energy equatorward. Wind patterns, unlike anything on Earth, might be acting as planetary-scale couriers, ferrying heat from the poles to lower latitudes in a relentless atmospheric relay. Then there's the ring rain theory. Cassini's final orbits revealed a shocking detail. Saturn's rings are actively disintegrating, showering the planet with icy particles at a rate of 10,000 kilograms per second. As these particles plummet through the atmosphere, friction vaporizes them, releasing kinetic energy as heat. It's like a continuous meteor shower, but instead of fleeting streaks, it's a steady drizzle of thermal fuel. The math is compelling. This ring-derived rain could contribute up to 30% of the observed heating, especially at mid-latitudes where the influx is most intense. But the plot thickens with Saturn's own internal dynamics. The planet radiates 2.5 times more heat than it receives from the Sun, a remnant of its primordial collapse and ongoing helium separation deep inside. Some researchers argue this excess warmth might percolate upward through atmospheric waves, massive pressure oscillations that ripple through the gas layers like ocean tides, dissipating energy as they go. These waves, invisible to the eye but detectable in temperature profiles, could act as planetary-scale whisks, stirring the upper atmosphere into a thermal frenzy. What makes this mystery so tantalizing is its implications far beyond Saturn. If auroras, ring debris, or internal heat can supercharge a planet's upper atmosphere, then gas giants across the galaxy, especially those with even more extreme magnetic fields or ring systems, might harbor similar thermal anomalies. Untangling Saturn's heat sources isn't just about solving a local puzzle. It's about decoding a universal mechanism that could reshape how we model exoplanet atmospheres. Every degree of unexplained warmth is a clue, a whisper from the complex interplay of forces that make our solar system's giants far more than meets the eye. Among Saturn's many moons, none share a relationship quite like Janus and Epimetheus, two celestial siblings locked in a gravitational waltz so precise it defies intuition. These lumpy, potato-shaped moons orbit so close together, they're separated by a mere 30 miles, less than the distance between New York City and Philadelphia. Yet in a cosmic feat of timing and balance, they never collide. Instead, like synchronized swimmers in a slow-motion routine, they swap orbits every 4 years in a maneuver so graceful it seems choreographed by the universe itself. The mechanics of this dance hinge on a delicate equilibrium. Janus, the larger of the pair at about 115 miles across, and Epimetheus, just 70 miles wide, chase each other around Saturn in nearly identical orbits. As the inner moon gains speed and catches up to its outer partner, their mutual gravitational pull twists the rules of orbital physics. Rather than crashing or scattering, they perform a gravitational handshake. The inner moon tugs the outer one forward, boosting it into a higher orbit, while the outer moon slows the inner one, causing it to drop closer to Saturn. In this exchange, they effectively trade places, with the original leading moon falling behind and the trailing moon surging ahead. The whole switch takes about 100 days to complete, unfolding with the precision of clockwork. What makes this phenomenon extraordinary isn't just the swap, it's the stability of the system. Most co-orbital configurations in nature are unstable, prone to chaos or ejection over time. Yet Janus and Epimetheus have likely maintained this rhythm for billions of years, their dance preserved by Saturn's gravitational influence. The planet acts like a cosmic conductor, ensuring neither moon strays too far offbeat. Even more remarkable, the moon's irregular shapes play a role. Their lumpy gravity fields create slight tugs and nudges that help maintain equilibrium, turning what should be a chaotic system into a model of celestial harmony. The aftermath of each swap leaves a tangible fingerprint. As the moons trade orbits, their gravitational jostling sends ripples through Saturn's F-ring, creating spiral waves that propagate like fingerprints in the icy particles. Cassini's observations revealed these disturbances, providing clues about the moon's masses and orbits. Scientists even suspect the duo's gravitational interplay might help shepherd the F-ring's chaotic structure, preventing its material from dispersing into space. Yet mysteries remain. Why haven't these moons merged or drifted apart over time? Some models suggest they might be fragments of a larger moon that split long ago, their current orbits a relic of that ancient breakup. Others propose their dance could be temporary, a fleeting equilibrium that might one day destabilize, sending one moon spiraling away or crashing into Saturn's atmosphere. For now, though, their rhythmic exchange stands as a testament to gravity's creativity, proving even the simplest forces can produce ballets of breathtaking complexity. As we watch Janus and Epimetheus trade places yet again, we're reminded that the universe often reserves its most elegant performances for the smallest stages. Saturn's birth certificate is missing, or at least hopelessly smudged. While we know the solar system formed roughly 4.5 billion years ago, pinpointing exactly when Saturn emerged from that primordial chaos is proving shockingly difficult. The planet itself offers few clues. Its gaseous exterior hides any telltale geological scars, leaving scientists to piece together its history through indirect evidence, and the clues we have don't always agree. Some estimates based on the chemical composition of its atmosphere suggest Saturn might be slightly younger than Jupiter, forming perhaps 100 million years later. Others argue it was born in the same sweeping era of planetary construction, with subtle differences in its core hinting at a more complex origin story. The biggest contradiction comes from Saturn's rings. If they were primordial, formed alongside the planet, they should be darker, littered with space dust accumulated over billions of years. Instead, Cassini revealed them to be suspiciously pristine, their ice gleaming like freshly fallen snow. This purity, combined with their rapid disintegration rate, suggests they might be a mere 100 million years old, a fleeting accessory in cosmic terms. But if the rings are that young, what catastrophic event created them so recently? One theory points to a shattered moon or a captured comet torn apart by tidal forces, a violent breakup that would have unfolded when dinosaurs still roamed Earth. Then there's Saturn's core, a puzzle wrapped in layers of metallic hydrogen. Unlike Jupiter's dense, compact heart, Saturn's core appears fuzzy, diluted with lighter elements like oxygen and carbon. This blurry boundary challenges traditional core accretion models, where planets grow by steadily accumulating solid material before grabbing gas. Some astrophysicists propose Saturn's formation was messier, a series of collisions between smaller protoplanets that left its core scrambled like a half-mixed cake batter. Others suggest it never fully finished forming, its growth stunted when the young sun's radiation blew away nearby gas reserves. The differences between Saturn and Jupiter are equally telling. Jupiter's stronger gravity hoarded more helium, while Saturn's looser hold allowed this lighter element to diffuse outward, creating distinct atmospheric layers. Saturn's orbit farther from the Sun also means it accreted more icy material, potentially explaining why its composition skews lighter. But these variations raise deeper questions. Did Saturn form farther out and migrate inward, or was its orbit always stable? Clues might lie in its trove of irregular moons, captured asteroids whose tilted orbits suggest a turbulent past of gravitational tugs and cosmic theft. What's clear is that Saturn's origin story isn't just about chronology, it's about context. Every anomaly, from its rings to its core, forces us to reconsider how gas giants assemble themselves. Was it born in a quieter corner of the solar system, or did it brawl its way into existence? The answers could rewrite not just Saturn's history, but our understanding of how all giant planets take shape in our solar system and beyond. From the hexagonal hurricane raging at Saturn's north pole to the vanishing methane lakes of Titan, we've journeyed through 25 of the solar system's most beguiling enigmas, and yet Saturn isn't done surprising us. This gas giant, wrapped in shimmering rings and surrounded by moons that spit geysers into space, refuses to fit neatly into our textbooks. Every answer we uncover, like the origins of those youthful rings or the secrets of Enceladus's hidden ocean, only leads to deeper questions. Why does Saturn's magnetic field align so perfectly while its radio emissions stutter like a broken record? How can a moon as small as Hyperion survive being half-empty space? And what cosmic clockwork triggers those planet-sized storms every 30 years? What makes these mysteries so thrilling isn't just their strangeness, it's the reminder that we're living through humanity's greatest era of planetary discovery. Missions like Cassini have handed us a trove of data, but Saturn keeps playing keep away with the truth. Its contradictions humble us, a planet so massive it could swallow Earth whole, yet so light it would float in water. A system where moons trade orbits like dancers and rings vanish faster than we can study them. These aren't just puzzles for scientists, they're invitations for anyone who's ever looked up at the night sky and wondered, what else is out there? So stay curious, whether you're Team Hexagon or Team Magic Island, these mysteries belong to all of us. Hit subscribe to join us as we unravel more cosmic riddles, because Saturn's secrets are just the beginning. Up next, we're diving into the icy giants, rogue planets, and black holes that defy logic. But before we go, drop your favorite Saturn enigma in the comments. Is it the phantom moon Peggy, the electric craters of Hyperion, or something we didn't even cover? The universe is vast, but the conversation starts here. Keep looking up, the next great discovery might be hiding in plain